All right, let's jump right into this explainer and build a rock-solid mental model of vertex distance. Whether you're prepping for your OCAPs, your written boards, or honestly just trying to avoid getting roasted by your attending in clinic, you absolutely need true clinical mastery of this concept. We aren't just going to memorize isolated formulas today. No way. We're going to understand the biological and optical processes that actually make these formulas work.
Here is our roadmap for today. First, we'll hit the core principles of optics. Second, mastering vertex distance. Third, some OCAP practice calculating power. And fourth, a classic board trap regarding plus lenses.
Okay, let's kick things off with part 1, core principles of optics. So to really get this, we have to start by understanding the far point. By definition, the far point is the specific point in space that is perfectly conjugate to the retina of an unaccommodated eye. Think of it like this. If you place a tiny point of light right at an eye's far point, where vergence is exactly 0, those light rays will naturally perfectly focus right on the retina. So what's the entire goal of correcting refractive error? It's remarkably simple. You literally just place a lens in front of the eye so that the lens's secondary focal point coincides exactly with the eye's far point.
And this brings us to what I like to call the 3 undeniable laws of refractive correction. First, unless you do refractive surgery, the distance from a patient's eye to their far point is physically fixed. It just is. Second, the distance between any given lens and its secondary focal point is entirely fixed by physics. And third, listen up, because if you remember only one thing for your boards today, let it be this massive, high-yield concept, the overlap rule. To give a patient clear vision, the lens's secondary focal point must overlap the eye's far point. Because these two distances are completely fixed, a specific lens power only works at one very specific distance from the face. If you move the lens, you miss the target completely.
Moving right along to part 2, mastering vertex distance.
So, what exactly is vertex distance? Well, it's not just some trivial measurement. It's the actual physical distance measured precisely from the anterior corneal surface to the back of the corrective lens. That precise specificity is exactly what trips residents up on oral boards. This physical distance is the missing link. It totally dictates whether your prescribed lens power actually hits that far point target on the retina, or if the focal point falls frustratingly short or long.
Now here's a massive OCAP pearl for you, specifically regarding the clinical threshold. When you're writing a spectacle prescription, if the power is plus or minus 5 diopters or greater, you absolutely must specify the vertex distance at which you refracted the patient. Why? Well, below 5 diopters, moving the glasses a few millimeters down the nose doesn't shift the focal point enough to noticeably degrade their vision. But once you hit moderate to high refractive errors of 5 diopters or more, every single millimeter dictates clinical success or failure. Even a tiny shift completely breaks our overlap rule.
All right, part 3. Let's do some active recall and OCAP practice by calculating power.
Let's test this with a realistic scenario. Imagine a patient whose far point is 20 centimeters anterior to the corneal plane. I want you to pause for a second and think, what is this patient's refractive error in diopters? Remember your foundational formula here. Really lock in your answer before we move on.
You got it. It's minus 5 diopters. Why? Because dioptric power is 1 meter or 100 centimeters divided by the distance to the far point. Make sure you're speaking clearly to yourself here. 1 divided by 0.20 meters. You always have to remember to convert to meters. Falling for the centimeter trap is such a classic OCAP mistake. So 100 divided by 0.20 is 5. And because the far point is anterior to the eye, we know this is a myopic eye, meaning the refractive error is a minus 5.00 diopters. Okay, building on that. Let's take that exact same minus 5 diopter eye, but now we're fitting them with spectacles at a vertex distance of 20 millimeters, which is 2 centimeters. What is the proper lens strength to allow for clear distance vision? Please don't just guess here, and definitely don't just blindly plug numbers into an equation you memorized. I challenge you to apply our clinical story and that overlap rule right now. Think it through.
Let's walk through the anatomy step by step. Step 1. The distance from the cornea to the far point is 20 centimeters. Step 2. We're placing the lens 2 centimeters away from the cornea. Therefore, subtracting that out, the distance from the lens to the far point is now exactly 18 centimeters. To obey our overlap rule, we need a lens that has a secondary focal length of exactly 18 centimeters.
And for step 3, we convert that back to dioptric power. 100 centimeters divided by 18 centimeters gives us 5.55, which rounds to 5.50. So the required lens strength is minus 5.50 diopters. This is a classic board question. I want you to notice how, as the minus lens moves closer to the eye, you actually need a stronger, higher minus power to push that focal point out to hit the far point.
Finally, Part 4, a notorious board trap involving plus lenses.
All right, consider this wild, high-stakes scenario. What if the only lens available on a desert island for this minus 5 diopter myopic patient was a plus 5.5 diopter lens? Is there any physical way to give them clear distance vision using a plus lens? Pause and think deeply about the properties of a plus 5.5D lens and our trusty overlap rule before you answer.
Shockingly enough, the answer is yes. Physics honestly doesn't care about standard spectacle frame designs. The overlap rule dictates that as long as we align the secondary focal point of that plus 5.5D lens perfectly with the far point of the eye, we hit a bullseye on the retina and we're going to form a sharp image.
Let's map out the anatomy and physics carefully here. Step 1, a plus 5.5D lens has a focal length of about 18 centimeters. Step 2, the far point of the eye is 20 centimeters to the left of the cornea. Because it's a plus lens, its secondary focal point is to its right, so we actually have to hold the lens 18 centimeters to the left of that far point. Step 3, just add the distances. The far point is 20 centimeters from the eye, plus the 18 centimeters from the far point out to the lens.
You add those up, and you get 38 centimeters. Literally, by placing this plus 5.5 diopter lens at a massive vertex distance of 38 centimeters away from the face, the secondary focal point overlaps the far point perfectly. The math works out, and the patient actually achieves a sharply focused image on their retina.
But here is the ultimate conceptual check, and honestly my favorite question to ask residents. Other than needing ridiculously unfashionable frames that stick out over a foot from the patient's face, why would your attending absolutely roast you for trying this setup in clinic? The math works flawlessly, right? So why is this an absolute clinical disaster?
Because true clinical mastery means understanding the biological consequences. At 38 centimeters out, you've essentially built a Galilean telescope. Sure, the image is perfectly sharp, but it arrives on the retina completely upside down, and their visual field is restricted to a tiny, tiny pinhole. So let's do a rapid-fire review of our top pearls today. 1. The overlap rule is absolute. The lens focal point must meet the eye's far point. 2. Always specify vertex for prescriptions of plus or minus 5 diopters or more. And 3. As a minus lens moves closer to the eye, you need a stronger minus power. Remember, you aren't just writing down numbers. You're architecting an optical reality for your patient. So I'll leave you with this to ponder. If moving a minus lens closer requires more power, what exactly happens to the power of a plus lens as a presbyopic patient slides their reading glasses down their nose? Keep your formulas handy, but keep your clinical intuition sharper. See you next time.